Initially, we understood the classification among force-based loads and the displacement-based loads. And we covered among the force-based loads, we covered dead loads or permanent loads. We covered variable loads consisting of live loads. So now we will move on to uh, other force-based loads. Okay. Okay. So are you able to see my screen? Yeah. Okay. So today we will move on to the next one, which is the next force-based load, the snow load. Okay. Now, obviously, the snow load is not universally applied. It is applied in the area where snowing is likely, which in our country uh, has application for very limited number of bridges, though I would assume that under certain circumstances we would have roads in Himachal Pradesh, possibly in the lower Himalayan reaches, maybe in the state of Ladakh, Jammu and Kashmir, certain places where there's a high probability of snowing. Now, uh, snow is basically atmospheric deposition of water, and it accumulates in various thickness. Uh, how many of have survived any winter in snow amongst you? Anybody is from Himachal or anybody who has lived through the winter season in snow
I have for a few days, sir.
for a few days? Okay. So my own personal experience is very old in the sense during my master's days when I was in US, and at that time the snowstorm in the city where I lived, okay, the snow was only 1 or 2 feet. That means we're talking about 600 mm or so typically. But in one city, in a place called Denver in Colorado, on the same winter storm, the it snowed for only 20 feet. 20 feet means you can imagine in places there was about a six-story building submerged under snow, that kind of situation. But we are not talking about generally in those kind of condition, transportation will not take place. So in our own code, that is in, as you can see in IRC 6, we have uh, two conditions: snow load with live load and snow load without live load. This picture gives you some incidence of what's happening when the snow is taking place. So what our code says is, if we have snow up to 250 mm, then you can consider that the wheel load and track loads are operating on the bridge simultaneously along with this load. And if the thickness of the snow goes beyond, 500 mm, then don't consider any wheel loads on it. Only consider track loading. So which means what? Track load essentially for us is only the 70R tracked. Okay. And in the next case is when there is a thickness in more than 500 mm, then you consider no live load. Okay. So the question to ponder about in the previous one, why the distinction? What's special about 500 mm that you don't need to consider? Why they have said don't consider wheel loads when there is a 500 mm snow on the bridge? What do you think would be the thought process? What do you think will be the philosophy that comes up with such a recommendation? So, uh, are you sure you don't drive in water which is 1 feet? 500 mm is 2 feet. You have your vehicles, you have seen them being driven in 2 feet of water. number of times. Buses keep going, flying in the city. Agree? Don't agree? In heavy rains. So why in the snow? Only tracked vehicle is looked at when thickness of the snow becomes 500 mm. Remember one thing, where those who genuinely live in places where it snows for a long period of time and that mobility is important, they change their tires. They change their tires called winter tires. I don't know whether you have seen it. They all are tires which have got chains and studs and things like that fixed on it, which provides them the grip. So don't worry about it linked to, something about not gripping and things like that. It has to do with this thickness, and it is not to do with the physical feasibility. What do you think could be? Any guesses? This picture gives partial hint of what would be the reason. Partial hint. Nobody wants to venture a guess. Okay, let's see if we can lead you to the answer. Uh, Typically, what is the height of a bridge parapet? 1 meter. 1 meter. 1 meter is around 3 feet, right? So if there is a 500 mm thick snow on it, how much of the parapet most likely to be visible? Most of it would be buried, correct? So the chances are, it's a safety reason why they don't want you to consider wheeled vehicles on that. Not that wheeled vehicles cannot travel on it. You can force to travel on it, but it's a safety concern that it might snow is just enough that it might be your parapet's visibility, especially when it is snowing. You also see the view is very foggy. You don't have a clarity. Your bridge edge may not be visible. So only a tracked vehicle, which has got a much higher, what do you call it, visual point, is likely to help you see the thing. So therefore, that. And finally, the last one, more than 150, more than 500 mm, it is basically the idea is you will stop all traffic. So that means, of course, in such locations, you must have a monitoring system which measures, which keeps indication of what the thickness of the snow cover, so that it can warn the motorists, don't go on the bridge. Okay. Now, so this has limited application in our country because most of our country is tropical in nature. Only sub-Himalayan regions, bridges located there might have the problems or design issues linked to loading due to snow. We move to the next force place loading, which is the impact load. So what are the impact loads that you are aware of? If you recall, when we did the summary, we looked at the vehicle collision on bridges, and we looked at the floating vessels impact on river bridges. So a good example of a photograph of a collision with the bridge structure, in spite of the fact that there are guardrails, in spite of the fact you can see that this truck has gone and collided with this trestle type of column. Now this impact loading is critical, especially if you have the clearances issue. Our code has got certain requirement which says if you have got a clearances up above this, or your substructure so much distance away from the carriageway edge, then you need not consider. Otherwise, you have to consider the impact of the moving vehicle on the bridge supporting structure, sometimes on the bridge also. Now, this vehicle collision load is essentially is a force, and I take you back to what do you call it, uh, your high school physics as to definition of how the force is to be derived. We all know that rate of change of momentum. Momentum means what? You had certain initial velocity and therefore you reduce it to zero. And its more important component is is the the duration within which this impact comes to zero. And that determines the magnitude of the force. So to understand that, typically our codes are all based on an operational speed of uh, 80 kilometers per hour. That is the impact. These forces are all defined for 80 kilometers per hour operational speed of the vehicle. And typically this vehicle weight, gross tonnage, etc. are defined which are likely to hit. It's again a probabilistic based design, and it has naturally two directions. One in the direction in which the vehicles normally fly, and one in a direction perpendicular to it. Now, coming back to this, let us say you have a pier in the on a road crossing. The question to you is, at that time, uh, would you consider what is your load, parallel or perpendicular? It depends upon your uh, the road going below. It is not based on the road which is going on top of your bridge. It is not related to that. It is related to the traffic on the lower level. So naturally, in the direction of the traffic at lower level, the velocities will be high. That means your initial momentum will be high, and therefore the change in momentum will be high, and therefore you have a larger force. And in a direction perpendicular to it, essentially it means it's coming at a small angle. It's a component, so it's a smaller magnitude is what it is described. Okay, and then it has got what they call it, two components. Now, can you explain what could be the logic behind the main component and the residual component? And remember, the main component is at the lower level and the residual component is at the higher level. Any explanation of for this kind of arrangement? And an explanation as to why this magnitude is lower. Yeah? Any idea? No rocket science involved, only common sense.
So the reaction from the superstructure.
No. The impact loading due to vehicle has two components. One is called the main component of, say, for example, let's take in the direction of the traffic is 1000 kilonewton or 100 tons if you want to talk in terms of ton, acting at a lower height, and a residual component which is 500 kilonewtons or 50 tons. It is acting in the worst position between 1 to 3 millimeters is what you do. Why this lower? Why this higher? Why this magnitude higher and why this magnitude lower is the question. What could be the logic behind it? Yes? Yeah, please. What could be the reason for this split up and what it could be the reason for their point of application. This question could be easily answered if you are all observant. Observant of what I won't tell, because that the answer will be in that. Observant, that's all. What load? So then why should I not have managed with one load alone? After all, your dissipation, that you're mixing up multiple terms. If you look at the definition I showed you that the force is created due to impulse by time, and impulse is the rate change of momentum. And change of momentum is initial mass into initial velocity minus mass into final velocity. Just a simple physics question. So dissipation is involved in the time. But why two components? And why two components at two different levels? Okay, I will take you back to a picture. This picture is also an example. This picture has some of the information, but because the orientation of the vehicle itself due to the impact has changed, so you may not be able to get it. And let me see if I can bring back the maybe I should share this picture. You're able to see the screen? Does it suggest the possible cause for two levels? Think. You are coming to that. If you notice, typically all the vehicles have a drive mechanism, which is a structure, which is the front part and a slightly behind the rear part. You see it? Almost all vehicles have. So with that, what happens? The first impact will be obviously the closest point. And if you look at it, the mass of it is concentrated at the lower end. And when this hits the support structure, what will be the initial velocity? Almost close to the full design velocity of the vehicle. Correct? And then by the time this gets crushed and the rear part, which are taller, if by the time they come in contact with the substructure, what happens to the velocity of this whole mass? It reduces. And so by the time the higher portion comes and hits the super substructure, its initial velocity for the higher component is lower than the front part. Correct? And if the velocity is lower, then the change of momentum will be lower. Rate of change of momentum will be lower, and therefore the force will be lower. And naturally, these taller parts will impact at higher level. Now, the design load is not considering any particular vehicle. It thinks a variety of tractor and the trailer units, and it gives you statistical equivalent. That is why you have two components to it. the lower component, which is called the primary one, and then you have the residual component, which is at the higher level. All right. So ultimately, now you remember one more thing about the impact load. We'll deal with that a little bit later when we talk about the design aspects of it. But right now, you keep in mind the important point is the force is lower if the time taken to uh, reduce the momentum from high velocity to zero velocity if the time is longer. And for the time to be longer, what do you need? From design point of view, what do you need? Do you need a very rigid substructure, or do you need flexible structure? That means deformability is an important criteria. Similarly, vice versa, to increase the time limit, do you need a very rigid vehicle, or do you need a vehicle that is more crushable? Difficult question. Obviously, deformation will take place in both the vehicle as well as in the structure. Agreed or not agreed? So therefore, vehicle also has a certain built-in crashability requirement that are built in, and the design forces are all done based. That is why, if you recall, vehicles have to undergo crash tests and they have to be certified for it. And that's one of the reasons where, if you look at the vehicles which all have, you know what is a bull bar? Have you seen these bull bars that people fix on their cars? Or rather, mostly it is done on their four-wheelers, four-wheel drives. You don't see it in the cars. Have you seen bull bars? Or you don't see? Yeah, yeah. In the front of the vehicle, they solder and weld and keep one metallic stuff. Correct? Have you seen it? Some people do it, not all of them. It just doesn't come from the original manufacturer of the vehicle. Users do it. Have you seen them being done? Now they are all illegal. Why are they illegal? They are illegal because they make the vehicle unsafe for the user. What it does is it prevents it, it adds to additional stiffness in the vehicle, leading to reduced crushability and therefore transferring a greater impact to the people inside the vehicle, and therefore it's unsafe for them. So I don't know if you are aware of it. There was a big drive in my home state of Tamil Nadu that the police were actually stopping all the vehicles which had all those things fixed, and they were removing them. They had a workshop maintenance guy who came with a welding machine. He was cutting and removing all of them, stopping the vehicle and removing them. Okay, so it comes from the impact load design criteria for the user as well as for the structure. We are looking at it from the structure. That other aspect which I mentioned to you about bull bar are all from the safety of the user. Now, the point is sometimes they also, very rarely, but sometimes they can also end up impacting the abutments. Now, as we said, there are two components. The larger we had an explanation, and perpendicular direction is a statistical equivalent, because obviously velocity perpendicular to the traffic will be much smaller. It will be only a component of the velocity. So they are only half, and basically it is a design prescription in the code. Okay. Now, these are all for the 60 kmph per hour velocity. This is in our code. Now the question is, if we want to use the same vehicles at a higher velocity, what should be the impact force? Yeah. What should be the impact force? Let us say, as I told you, these are all prescribed on the basis of a crash test done at 60 kilometers per hour. But we have people who drive all these things at 100, even higher. And if you go to European autobahns, there's no speed restriction, and you can even drive at 200 kilometers per hour if you feel safe enough. Vehicles are also designed that way. Then what happens to this impact force? Yeah. And how much will it increase? It will be directly proportional to the velocity if you assume that the time of application of impulses remains the same. But quite often what happens at the higher velocity, the time of application of impulse also crushes, because the with the higher velocity, with the higher force, the crushing is faster, not slower. Okay. Therefore, for safe driving, always follow the speed limits. It's good for you, it's good for the vehicle, it's good for the structures on the road. Right? Now, you have the vehicle collision as a point of application as it described below. Then there is the what do you call it, the normal one you apply and the residual one which you apply at the due to this is in the longitudinal direction, and in the perpendicular direction also you will have the uh, smaller values. Okay. Now, uh, in this direction, it's just a visual impact on the both of them. Now, the nominal standard traveling vehicle at 60 kilometers per hour, when the speed limit is reduced to below that, but it can never be really reduced considered on that. Now, the considering the effect of collision on bearings and foundations, but not on abutments, because abutments which have a very strong either earth retaining structure or quite often are protected and are far away from the carriageway. So therefore, the impact collision load on the structure is not. And it have to the collision loads on bearings is important because it can lead to dislodgement of superstructure. Now, the magnitude of the vehicle collision load on superstructure is a different definition, and it normally it's not defined in our code yet. But if you go and look at the BS code or in the Eurocode, they do have a definition of the impact load on superstructure. Okay, so for us, it primarily is on substructure and foundations. We move on to the next type of impact loading, and what is called as a floating body impact. What you see is a picture of a barge which has hit the bridge pier, and it has brought the whole superstructure down. Now, this kind of a event happens, as is obvious, where there is a traffic in the water flowing below the bridge. So you can see a number of examples that are done. For example, if you take a look at this bridge here, what you can see is that the bridges, the foundations have been protected by installation of additional impact bearing structures. Okay, and then you have a solution of a design of this nature where there is none. Maybe they will install it later, but normally it makes sense to do the construction at the time of the installation, at the time of the construction itself. The question is, these kind of structures which are called fenders, they are the ones which help protect the bridge foundations from being directly come under the impact of any floating vessels. They protect the bridge. And there are certain characteristics that these fenders must take care of. So one good example is an earthen fill island. Basically, these, if anything impacts this, these are deformable. And when these are deformable, then what happens is, just like if you look back at the expression for the force of which we discussed as the rate of change of momentum, same thing applies here also. The velocities are little low in the sense that generally on places where bridges are constructed and the ships go or barges go below, The velocities are all in the range of 6 to 10 knots, and that may be around about 10 to 12 or 15 kilometers per hour. But the floating barges are very heavy. So therefore, the amount of energy that they will transmit to this is much larger. So you need a larger dissipating arrangement. So you have this island and they deform a lot. So one solution is something like this. Other solution, one example of it which you can see here, is a question to be asked is this a good solution? Wherein they have added additional piles on the upstream, downstream, wherever the possible impact can be. Is it a good solution? Is such a fender good? If so, why? And if not, why not? Why does the fender, in this instance, why does the fender have to break before transmitting the force to the structure? If you can look carefully, this fender is connected here. It is essentially additional piles. If you can notice, it's connected. It's only additional piles. So what they have done, they have basically strengthened the foundation. But does it mean that it is safe from impact? Obviously, it will undergo significant deformation. Now the question is, how do you design these fenders? Should they be designed elastically or inelastically? You understand the difference between elastically designed fender and inelastically designed fenders? Yes, please. Nobody wants to venture out. Should the fenders be designed elastically or inelastically? The question. I think I have to repeat my professor's lessons to me in structural analysis to all of you. That the deformations are reality and the forces are conjectures. So how does fender protect? They have to be designed elastically. I have feeling now I'll have to take a class on what is elastic design and what is inelastic design. Does elastic design permit large deformations or inelastic design permit large deformation? Yes, please. So fenders should have large deformation or not large deformation? What do you mean by nah? Once you say it is, I think so. Okay, so it should not deform much. If it doesn't deform much, then how will it absorb energy? If you recall, ultimately a moving body has certain kinetic energy. That kinetic energy is going to get absorbed when it comes to a halt. It has to be transferred to somebody. The whole kinetic energy will get transferred to the structure. So the structure will be displacing and it will be work done. Work done is force into displacement. You are designing for force. Work done will be force into displacement. If you want the force to be small, the displacement must be large or not? No. Sukalyan, I wanted you to think through all this process. So don't, I have a feeling you're all confused with what is elastic. Your ultimate limit state design is an elastic design. Do you know that? So whereas your ductile detailing, is it in elastic design or inelastic design? So why do you do it? Why do you do it in earthquake engineering? Not we face, we want large deformation. We want large deformation. So fenders, we want large or we want small deformation in fenders? So we should design them inelastically. That means we have to introduce plasticity in them, large deformation. But at the same time, what should it be? Then in that case, should the fenders be close to the real foundation or far away from the foundation distance or the zone of influence? Should the fend far away? So now comes the question. In that case, this design, is it good or is bad? It is bad. Okay, go back to this. This is good because they have built in inelasticity in the deformability of this island. This is good because they have provided inelasticity and deflectability in these blocking structures which have a large gap from the main structures. Thereby they have to deform a lot before the ship hits this or the floating body hits this, as is the case with this. Okay, and remember one thing, it should generally be all around rather than one or two in one direction. Okay, so these fenders need to have certain configuration. So you have a floating body which can impact at its level above the water line, and it will undergo localized crushing and deformation, or this is a barge type impact and this is the ship type impact. Ship can impact at the higher level, barge can impact at the lower level. So there's a whole range in which the floating bodies can impact the substructure and foundation. So to prevent them, we need to have independent foundation. This is one solution. This is not the only solution. And the solution actually depends upon the magnitude of the force and the kind of vessels that are flying in the water body. Okay. So generally, the conceptually is you have to have an independent foundation. There must be sufficient gap between them so that it deflects without hitting the foundation. Similarly, this and it should have certain height so that it can handle both the low moving vessels and the high height vessels, preventing them from impacting this. So configuration is important, and the configuration will be decided by the kind of vessels that are plying in the water body. That is the important thing to note. Okay. Now our code, what does it say? It classifies the navigational channel into categories of different vessels. Okay. And our code says that it should act at the height 1 meter above the height level. These are the forces defined for in IRC 6. Why are they designed like this? Because IRC 6 is not applicable for bridges built in marine condition. These loading standards are built only for river bridges, wherein it is anticipated that only freight traffic in the form of barges will be carried out. I don't know how many of you are aware. Right now, there is supposed to be inland waterway operationally carrying freight from more or less along the Hooghly, Calcutta till Varanasi through the Ganges River, through the navigational channel created there. So it carries barges carrying the cargo from the coast to the interior land. So that is river water, obviously, because the depth of water cannot in all the seasons cannot be 15 meters, 14 meters, because it's a 3, 4, 5, 6 meters is all that is guaranteed. Big ships cannot operate. So in India, our code is divided into, is applicable only for barge traffic. We are not in a position to design for large cargo ships which can carry almost 2 million kilonewton dead weight. Or when you do this, you need to refer to specialist literature. But for our code, what does it do? It designs the load into uh, so many of these barges. All right. And the design forces in the various categories are given like this. And if I'm not mistaken, if the category of the water body is unknown, we are supposed to design it for a minimum of this category 3. If I'm not mistaken, I don't recall the code exactly, but this is the minimum requirement. Otherwise, it will be you will find out from the inland waterways notification which stretches of which rivers are categorized for what kind of traffic. And in our case, our traffic is not the road is not based on the size, the deadweight tonnage of the ship, but on the physical dimension of the barges. Okay, so these is the range of, that means if you talk about it, it's about 4,000 ton, 2,000 ton, and 1,000 ton. 1,000 tons is the bare minimum for any navigable river. Okay. Now the question is, this force is also normally to be provided only in the to be considered in the design of foundation for what are known as navigational spans. It need not be applied on all the substructure and foundation. Okay. So it needs to be applied only on the navigational span. So that means there is a definition required of which spans are navigational. That depends upon individual bridges. Okay. And the considering the fact that our magnitudes are small, it is meant for barges. It's only 2% of the largest DWT that we are talking about. But that's because we don't expect such large vessels to ply in our rivers, and therefore do not take the barge impact forces that we are given in IRC 6 to ship impact for collision forces. In case you are designing something, say for example, if you are a Trans Harbour Link bridge designer, which is connecting Bombay Island to the mainland Bombay, and it crosses the navigational channel of the ships coming to Nhava Sheva port, JNPT port at Nhava Sheva, to the sea. At that time, you have to have a specialized study to design what kind of ships will go there, and therefore refer to and do the design of the foundation for that impact port and not use the forces listed in our code. Again, clarify, the forces in our clause are given only for riverine traffic related to usage of barges. Okay. So for actually ships, you use the actual force, but for our code, we will use it as designed forces as given in the code itself for river bridges. And generally, the good idea is to protect the piers by independently supported structures adjacent to the pier, and they should have sufficient capacity to absorb energy before the vessels hit the pier. The question happens is, our foundations also have some residual strength, but the idea is if our initial independent structure slows down the vessel and brings it nearly to halt, even if it hits, it will hit with a very low velocity, and therefore the amount of force transmitted to substructure will be much smaller. Okay, therefore it is essential to plan out the fender systems for the substructure and foundation adjacent to it with sufficient gap between the real substructure and these systems, so that you have what is called as a distance of influence. Okay, you can have fenders, artificial islands, sacrificial caissons, and also sometimes when I say fenders are for smaller forces. It is also possible to utilize the inherent strength of the foundation, but just preventing local damage by putting up a rubber arrangement which absorb and slow down the impact. They stretch the time of the contact so that the velocity of the vessel is brought to zero over a longer period of time. Therefore, the forces are reduced. So those are the special rubberized fenders that are designed for. So sometimes they are also used on the bridge foundation. And many of you would have seen this picture of a famous recent accident last year about a ship hitting the main span of a bridge in Baltimore in United States, and the foundation got broken and the whole superstructure came crashing down on this ship. So it's not that it doesn't happen, because accidents do happen, and this is inquiries going on as to how they lost the control, because this is a very commonly used navigational channel. There are all kinds of buoys and markers which tell which direction the ship has to fly. Yet this happened. Okay. So from uh, ship loading, we will move on to the uh, next set of type of force loading, which are the wind loads. Okay, wind loads are little more complex than the other force-based loading, because the response of the structure sometimes depends upon the um, stiffness of the superstructure itself. So the wind load is not something that is an absolute definition, but we do have a certain kind of absolute definition used in our code. But in highly flexible structure, response is much different to the wind loads. Okay, so all of you would have seen this very famous. We'll come to this Tacoma Narrows Bridge a little later. Now, the horizontal forces on due to wind in our code is specified based on the intensity of the wind velocity, and the force is calculated on the basis of the elevation of the bridge deck or substructure which gets exposed to the wind. Okay, as area seen in there, this is the basic what they call it criteria. And in the case of parapets, if they are of the perforated or railing type, then you have to consider only the block, the obstruction area. That is a typical concept to be used when assessing the estimating the wind loads on the superstructure, the horizontal force of a specified intensity. How do you get the specified intensity? Now, if the case of that was for a bridge with a solid elevation, okay, and now suppose the bridge is not of the solid elevation, and it is, say, if it is like a truss, then what happens is, then the wind is coming from the transverse direction, then the truss wind forces are divided into two parts. The one closest to the wind direction is called the windward truss, and the other one is called the leeward truss. So what happens is, the total area that will see the wind pressure is the net area of the windward truss plus half the area above the deck of the truss, which is shielded by the windward truss. But therefore, some effect is seen also. It also depends upon the distance between these truss. So if you have a wider and wider deck, this half area might increase. It can go even to as much as the full area, depending upon the distance between them, because the shielding effect of this truss, this members of this truss, gets eliminated by the distance between these two. Okay, so in through bridges, exposed area is calculated differently based on net area rather than the full gross area. But in the solid structure, in this kind of structure, it is the total exposed area that is used for calculating that. Now, wind load also has other effects, which are like, for example, when the wind load blows over it, and as you have seen, if the bridge deck particularly has an aerofoil kind of section, then what happens is that the velocity of the wind above the deck and velocity of the wind below the deck, they're different. Like the way, if you want to look at the closest parallel to want it, you can visualize how an aircraft takes off. As the way aircraft moves faster and faster, the shape of the wings, which are called the aerofoil shape, they are in such a fashion that the velocity of the wind on top of the wings is higher than the velocity of the wind below the wings. So then by Bernoulli's principle, wherever the velocity is higher, the pressure is lower, and therefore what happens is the lift is generated. So apart from the transverse direction forces on bridges, you also have, due to the flow of the wind around the deck above and below, you also have a possibility of uplift or downward pressure. Both are possible. Both are possible, and that's an additional force that needs to be considered. And the how to calculate is defined in the code itself. Then you have the we have wind forces with the presence of live load and wind forces in the absence of the live load. So in the case of a roadway bridge, the wind force is considered to be on the live load is considered to be acting 1.5 meters above the roadway, and you need to consider additional 3 kilometer for the on the vehicles itself. You have to consider this kind of a force according to IRC6. Rest assured that this IRC6 is undergoing a significant revision. I don't know whether the revision is already published or not. It was almost ready for publication last year. So there will be significant changes in the wind code according to IRC6, which will be more in line with IS 875 Part 3, which is related to the wind code. So that will be what this code is going to slowly move towards that. Okay. So we have to consider the wind load on the cross section of the deck. We have to consider the wind load's uplift effect on the deck. We have to consider the wind loads on the live load which is flying on top of the deck also. Now, our code says that when the wind speed is more than 130 kilometers per hour, basically this is 39 meters per 36 meters per second. I don't exactly know. I can calculate and check. I think it is 36 meters per second. There should be no wind load considered on the bridge deck, basically from safety point of view. 36 meters per second. So bridge decks have to be obviously, which means that now 130 kilometers per hour speed. Normally, when do you expect to see this kind of effect? You will expect to see in the case of a severe cyclonic storm. So most of you may not have seen it. Those of you who live in Chennai or the East Coast could have seen this on a regular basis during the this now October, November, December season. There are a lot of cyclones that hit the east coast of India. So we see this, and in fact, at one time we have also seen wind speeds of 240 kilometers per hour about 2-3 years back in the city of Chennai, when the cyclone crossed very close to the city. So whenever the speed is more than 130 kilometers per hour, live load should not be considered, because live load is expected to be monitored and stopped. Nobody would attempt to do it. Yeah, but you can always assume that there'll be a few people who will break these rules and still fly, but that's at their risk. But otherwise, as a designer, you don't have to consider live load whenever the wind is more than 130 kilometers per hour. What it means is, in the combination of live load that you check your design for, if you are considering the live load as the leading load, then the associated wind load should be calculated for limited to a wind velocity of 130 or 36 meters per second. But if you are considering an empty bridge, then you have to consider the maximum wind load that can occur in that location. Okay, and the maximum wind load map of India is there in the code itself, as you can see, and we have basic wind velocities ranging from 33 to 55, and most of the 55 you can see is on the east coast and some parts of northeast. Otherwise, you have mostly 50, 47, 44, and a few interior regions which are don't have much wind, and therefore they are designed for 39 and 33 also. But significantly, 55 to 47 is the majority of the area, and 55 being mostly along this coast. I don't know. I think a part of Gujarat coast is also, because this is also cyclone prone. So these two are the zones where you'll see 55. Otherwise, mostly you will see 50 and 47. So this is given. So once the velocity is given, you will the pressure diagram variation with respect to the ground is defined in this fashion, and the pressure is proportional to the square of the velocity, and you can say that and the reference velocity is used at below 10 meters. It is, though it's drawn from 0, essentially you should consider it as a constant up to 10, and then you can consider the variation like this. Up ground to 10 meters, you consider this much. Now if you take a look at this, If you translate this into megapascal, what do you think is the order of wind pressures that you're seeing? How much is this in megapascal? Huh? No. I don't know whether I have made a mistake in Newton or. Yeah, kg. Yeah, you're right. It will be very, very small values. Okay. So this is the kind of wind pressure you have to consider. But this basic pressure is not necessarily the most critical aspect of it. These terrain categories are currently not what, at least till the amendment is issued, will not be, you will not get a table like this. You will have to now calculate, the wind pressure is dependent on the four factors K1, K2, K3, K4. Have you seen IS 875 part 3? How many of you have referred to IS 875 part 3?
I referred, sir.
You are referred to it. For the building design, you generally do it, right?
Uh, Here for metros and all
Right.
IRS.
Because you are doing the station building, you will be definitely referring to that, correct?
Sir.
But for bridges, you generally don't do it. You are directly given the pressure. For metro, if it is referring to IS 875, you will have to do it. But road bridges, we have the pressure defined directly. Now question comes, you will have to refer, once the amendment comes, you will have to go back and uh, locate all these parameters and then come to a conclusion about the pressure. So basically the velocity depends upon four parameters, K1 to K4. You will see that later on the code when we see that a little bit in detail. And the pressure is not significantly very high. These are all, as you can see, 75 kgs, 80 kgs per square meter. It's not a very large pressure at even the highest level. On the railway, it is a little more problematic in the sense that the obstructed width of the live load itself is very large, whereas in road bridges you have gaps in between vehicle. In the case of live load in the railway bridges, virtually there is no gap and the whole live load has a large obstructed width. Plus, more importantly, wind load is also significantly affected when you have valley situation wherein the natural terrain channels the wind going across. So there are enhancement. That is what will be the part of the various factors that are defined in IS 875, which are not there in the bridge code. Our bridge code, road bridge code doesn't have anything like that. Okay. Now, in the railway case, as you said, because you have this wind acting on the whole of the live load, there is also a stability issue, which is when the railway operations are far more rigorously controlled during the high wind situation, because high winds can lead to the instability of the coaches itself, because the supporting bases are typically the gauge of the rail, and if they go very high, then they become problematic. So the structure's response to wind is little more tedious because the there is the what do you call it, the wind introduces the transverse shaking of the bridge. What does it mean? A wind blows and then if it stops, the bridge, due to its flexibility, will continue to shake. So that means there is a dynamic aspect to the wind, which then depends upon what? It depends upon the natural period of vibration of the bridge deck itself. So when does this become important? You can have resonance. That is a different matter. The question now is, for the wind bridges, uh, uh, what kind of natural period should we target? Large or small? what kind of target time period, natural period should we target for limiting the wind response? We need to target to have smaller deflections. That means we need to target stiffer structure. That means we need to target smaller time periods. It goes in conflicts with the other force which we'll come to later, which we need to target larger time period. So we'll have to look at the balance both of them. So basically the lateral natural period of the bridge becomes an important one. That means particularly for our tall substructure and foundation system in valleys, it becomes the dynamic aspects of wind become a critical issue. If you think in terms of suspension bridge, the deck is here. All the stiffness is provided by the stiffness of the vertical cable only. So this bridge has got a very low, very large time period, very what do you call it, large deflection possibilities. And you need to do, for such structures, you need to do the natural mode shape analysis. All the natural frequencies has to be estimated and then study the wind characteristic to prevent certain type of failures, which Sukalyan mentioned, related to resonance of the bridge deck with the wind velocities. Now, in the thing that you have to remember carefully is the wind induced resonance is caused when the wind velocities are wind flow is steady flow or turbulent flow. Wind induced oscillations will become critical when the wind is blowing steadily or when the wind is blowing in a turbulent fashion. Laminar flow or turbulent flow, if you want to understand in those terms. Not sure. Okay, we'll park the question. We'll come back to it a little later when we have a little better understanding of it. Okay. Now, what you're seeing here is a very famous bridge, but you can imagine that this kind of this is introduced by a bridge deformation. I will stop this and I will share with you another what do you call it video, or much more famous. I don't know whether you have seen it or not, but even if you have not seen it, it is even if you have seen it, it is worth watching. But you should let me know whether you are able to hear the sound. That is more important. Are you able to see the video? But are you able to hear the sound? Okay. Basically, what he is telling is this picture is taken when the wind was blowing at 35 miles per hour. Okay, 35 miles per hour. Remember that figure. Okay, so 35 miles per hour. What do you think is the wind velocity? If you divide the miles take the miles as 1.6 kilometers per hour. 35 miles per hour is somewhere around 20 kilometers per hour, which is a normal wind anywhere in the world. It didn't require that high velocity of 130 kilometers per hour, etc., to break this bridge. Of course, this bridge was constructed in 1940. Within 6 months of its construction, this incident happened. They didn't understand the wind behavior, wind phenomena, the dynamic response of the wind that much better in those days. This bridge has been reconstructed with all the stability, safety feature, but essentially the point to note is that ignorance can lead to this kind of a situation. Commonly, this is just an extract of the same video, but I didn't want to play this. So basically, this kind of a phenomena takes place. This is there are many phenomena like buffeting, galloping. We'll understand the terminology when we look at the wind load in little more greater detail. So you see the collapse of the structure basically because the dynamic aspects of the bridge were not understood well in those days. And we are talking about 1940. That means we are talking about almost 80, 85 years back. So the crosswind impact, that is, 55 kilometers per hour speed, it is only 15 meters per second. So you're talking about, very, very, in the sense, a small level of wind velocity. When you see the, whenever you have a cross section which has multiple girders, the kind of behavior that you noticed in the other Tacoma Narrows Bridge video takes place wherein small eddies are set up, wherein the bridge undergoes torsional swing until it exceeds the capacity. So you should avoid these multiple girder kind of situation in very long span. Your longer span should typically be more or less aerodynamically shaped structure with closed section, so that you avoid setting up this crosswind eddy oscillations based on that. You remember one thing, it's also an important role is also played by the designing and detailing of your crash barriers. And of course, when I say it's not, if your structure is very stiff, this is not a problem. This is a problem only if your structure is very flexible. And therefore, for flexible structure, you need to do a lot of dynamic analysis. And if you have done before you do any great amount of detailing, if you do the dynamic analysis and find out the first the primary modes and study them and make sure that they are all behaving in decent levels and the velocity at which they will get triggered. If you understand that, then you can do the detailed design. Otherwise, you will end up wasting a lot of time. But again, typically not required for most bridges, but definitely required whenever you go for longer and longer spans. Now, in the transverse shaking that you saw in the thing, it is triggered by the presence of multiple girders. Making this into two equivalent shapes like this is not necessarily the good idea. It still is two girders, and there is a space here, and you can have vortex shedding here. Ideally, you should shift to the third cross section for long flexible structure rather than ever go for this girder and slab. It may be just of interest to note that the longest span currently in existence in India, that's the Bet-Dwarka cable stayed bridge, had similar issues which are flagged during the wind tunnel testing of the cross section, and they had to introduce what we call it aerofoil sections in sections of bridges to alter its dynamic behavior so that the resonance doesn't set up for that bridge. Okay. So moving on to the from wind load, we move on to the water loads. Now water load has got multiple effects that we need to consider. As you can see, this bridge piers are an obstruction to the flow of water. When they go around it, naturally they will cause a direct force on it, which is called the water current forces. And there are other additional effects that also come about due to the flow of water around it and the presence of water itself. One of the effects that comes about is the buoyancy. And the buoyancy, as you can know, is counteracts the gravity effect. It has got different implications in the different locations. And Archimedes' principle is the same thing that is used here to determine its effect on the structural component. So when you take a bridge like this, if the superstructure is submerged in water, if it is, I'm using the word if because we are theoretically allowed to design submersible bridges in our country, but nowadays very few people design submersible bridges, which means we always want to design high level bridges. So superstructure is never submerged. But if it is submerged, then what kind of buoyancy effects that you must consider on the first we look at the substructure. When it comes to foundation, you must consider the buoyancy effect on the 100% of the components that are submerged in water. But when it comes to checking the structural design of any of the RCC or masonry structure, then we need to consider only 15% of the buoyancy effect on those components. Say, for example, we want to check the stresses at this location, at this level. Then the amount of substructure that is submerged in water is this. Then the buoyancy effect to be considered there is not 100% of the volume of the fluid displaced, but it's only 15%. And this rule is given in the code primarily to say that yes, we are designing these structures and these structures are being designed as crack section. And because of the cracking, there could be pores in it through which the hydrostatic pressure can apply. And we are estimating that the pores will not be bigger than 15%. That is why for structural design of substructure, you take 15%, but for the base pressure check, you take 100% buoyancy. You need to consider it for superstructure also in case the water level is above the superstructure, as the case may be in the case of submersible bridges. Okay, so you take 100% for the superstructure also in that case. It's a very specific case when you are doing the submersible bridges. Now, there are other forces that will happen. There is a what do you call it? A hydrodynamic force, which is a dynamic effect of this, which is particularly happens when the foundation is subjected to vibrations and displacement in water. But due to the dynamic effect of the water flow around the pier itself, you end up creating a horseshoe shaped hole, which is called the scour hole. This cover happens additionally around the pier due to the fact that the velocity of flow is altered. And as we saw in the case, because in any transverse flow, these obstructions reduce the area. So near the pier, the velocity is higher than when the pier is here. And again, the velocity reduces as it goes out. This effect gets vanished. So some distance away from the foundation, the velocity goes back to the average velocity. So there will be an average cover. But there are localized scour holes around the pier. It is in the shape, generally in the shape of a horseshoe, and these are caused by the fact that the higher velocity, when they come here and suddenly find a lower velocity, they set up what is called as a vortex shedding or an eddy current kind of a thing that takes place here in a clockwise fashion, and they erode additional soil localized to the foundation. So this effect essentially leads to an erosion, very large erosion close to the substructure, and reduces as we go further and further away from the foundation. Okay, so typically what happens is let us say that we have a bridge, and we are assuming that this is a stable bed, but when you put the bridge piers in it, you are creating an obstruction. And when you create the obstruction, there is something called an additional scour that takes place overall sen. Of course, this overall scour could also take place in case this bed is also silted up, and during the flood, the velocity is sufficient that it can remove the silt. So this is the case. It may be the case even with the absence of the bridge, but with the presence of the bridge pier, what happens is there are localized scours which go deeper. Not necessarily, I've just indicated it right up to the well cap, but not necessarily, but something additional will take place. So what happens due to this is that you lose soil resistance in that zone, which is critical for our foundation design. That's the whole point in understanding that apart from the direct physical force that is created by water, it has other effects such as cover to be considered in the foundation. This is not so much to say that this is a load, but it is an additional effect that comes out of the presence and the flow of water. Okay, this flow of water can also affect the what do you call it, embankment. They can erode embankments when the water flow is like that, and when the eddy current takes place here, it can erode the downstream toe of it, so which needs to be protected. How do you calculate the water pressure? So there is a, again, just like wind pressure is directly proportional to square of the velocity because it's also based on the laminar flow concept. Water current is also the force is the pressure is proportional to the square of the velocity. So into a constant. This K is the pier shape factor, we call it. So if we want to look at the water current forces, we have very little say in what we can do about the velocity because it is controlled by the nature. But what we can do is the amount of force that comes on our pier, we can control it. How can you control it? By controlling the shape of the pier. So when you look at the shape of the pier and you look at the values of various, the smallest one you get is a triangular cut and ease water. What it means is you have a triangular, and if you have a curve as a part of a equilateral arcs of circle, if you put up instead of straight, if you put a small circle here, that kind of one has the least what do you call it, ease water, and simple triangular 0.5 and probably goes up to a maximum 1.5 for the square sections, absolutely rectangular space to the flow of water. When that happens, the force. So we have, as engineers, we have only control on the shape of the pier, and even if you take a look at the circular section or semicircular section, our K value comes down from a square of 1.5 to 0.66. So between that is why if you notice, generally in river situation, we tend to go for circular. Though technically, from structural engineering point of view, circular sections are not very efficient, but we still do it in order to reduce the water current forces where it is significant. So the variation of the water current forces over the height is defined in the code as a linear of the V square. V square is linear from maximum at the surface to 0 at the bottom. Basically, from the hydraulic study, you will get that kind of a thing. And therefore, the velocity, if you know the mean surface velocity at different height, it is proportional to square root of x from the top, x from the bottom to the h itself. So this is how the variation you can, but if you look at V square, you will get it as linear from 0 at the bottom to the maximum at the top. That's how you will get the velocity variation, square of the velocity variation, and therefore the pressure will also be linearly varying because it's proportional to the velocity. Okay, code asks us to consider transverse direction of water flow and also consider a 20-degree inclination in the water flow because our bridge piers may not necessarily be aligned perpendicular to the bank. That's one situation. Also, due to the fact that the rivers are not absolutely straight line all the time, they keep meandering. So that means there's always a component of the water flow which will be not directly channeled along the direction perpendicular to the bridge. They may be having small inclination. To cater for those kind of variation, the code asks us to consider a 20-degree inclination to the force also as an additional load case. Okay. Then we move on to the seventh type of pressure loading, force loading, is the earth pressure. This comes about due to any retained structure. When we have a retained structure and a fill, we have earth pressure. We have number of theories. You have Rankine's, Coulomb's, etc. to tell you how to calculate the pressure. Code also gives you an expressions for that. So the soil fill behind an abutment is a classic example of an earth pressure that we have to consider. Generally, abutment will be the one which will primarily be affected in our bridge structure. And the code also says under no circumstances should you design for any retaining structure for a pressure less than 4.8 kilonewton per cubic meter density. That means equivalent hydrostatic pressure, considering the fluid has a density of 4 point. Now, you should not design for anything less than that. And you have Coulomb's theory for non-cohesive soil. You have Coulomb's theory with Bell's correction for cohesive soil. And then you have Rankine's theory for soil at rest. These are the various theories that have been given for us in the IRC to withstand active and passive resistance. And in the case of a non-seismic condition and in the case of a seismic condition, we have the pressure. So define the in the case of a passive condition, this alpha is a value related to the slope of the wall face, beta is the inclination. These are the pressure in the case of a non-seismic condition. A modification factor is given in the case of seismic condition, introducing an additional parameter called lambda. What is the effect of this seismic condition? We'll see in the next slide. I'm going too far because these formulas are all given in your code itself. Okay. So generally you have earth pressure at rest. So generally tend to use Rankine theory to calculate the pressure. But if the earth moves towards the wall tilts. At that time, active pressure is generated on the wall, and in the case the wall pushes against the soil, then you have passive resistance developed in the soil. So the pressure is developed like that, and then when the ground acceleration is downward, that means the earth is accelerating downward during a seismic event, then what happens is the active pressure increases and your passive resistance decreases. This is the principle that you need to remember clearly about the thing and when you're using the expression there. And obviously the role will reverse in case the acceleration is upward, and in a seismic event, you know that both are possible, upward acceleration as well as downward acceleration. Okay. Just give me a small quick break. I'll join you in 2 minutes. Okay. So we were on the earth pressure loading. So we need to design the abutment and retaining wall for this. Automatically, along with earth pressure, we design for surcharge, live load surcharge, which is for the abutment is equivalent to 1.2 meters of earth fill, and for returns it is half of it. And we also need to design this in order to reduce the water pressure due to any accumulation of water. We provide for weep holes. Plus, remember, these weep holes are important only for abutments which are abutting a river, so that in case the water table during the peak flow, if the water level is here like that, then what happens is the adjacent soil will also get the water table, and if there is in 2 or 3, and water is a much poorer flow media than the main river itself. So as soon as the flood passes, the water level from high flood will come down to the normal flood level, but the water table will be retained in the soil, and if it is not drained, it will create hydrostatic pressure, additional force on this, which we want to dissipate. So in order to minimize this due to submerged soil, we allow for the weep hole. These weep holes, however, don't make any sense if provided in the urban flyovers, unless you have an open area through which the water can percolate down. Then that case, at the bottommost level, there can be on dissipating level. Otherwise, normally this requirement is only for river bridge. Quite often, many of you might have seen drawings made in which this is provided in all kinds of retaining structures, including retaining wall for the embankment. They will be shown for box culverts, all that. Okay, not necessary, these weep holes, but it's definitely required for the abutment on the river bridge. Okay, now we come to the next force load, which is the blast load. As the term indicates, The blast load is caused by an explosion. An example, you can see here, an explosion has. Sorry. I'm sorry. I thought I was sharing it. Now visible, my screen? Okay. That's an example of a blast at the substructure. The whole thing has, concrete is gone, therefore the whole thing has sunk down. Okay. So an effect of what is the effect of a blast loading. So if you look at it, you go back to our summary of the components of a bridge system. Can you suggest which is the weakest component in this whole thing? We have superstructure, bearing, substructure, foundation, and soil. Among all these 5 components of a bridge system, which component is the weakest? Why? Why is it the weakest? Others know the answer. What is the reason they think? Or do you agree with Sukulen that bearing is the weakest? Or does anyone if you have other opinion? Yes, please. Why is bearing the weakest? If you agree, why is bearing the weakest? If you disagree, what else is the weakest? What happened today? Everybody is silent. Okay, you think about it and you get back to me later to tell me why you think bearing is the weakest. All right. So, identification wise is okay. Now we look at the effects of blast loading. What are the various effects? Now, typically, blast is in the air. Essentially, blast is essentially a pressure wave created in the air initially. So, whenever we have an explosion, a primary pressure wave starts. Okay. And then this pressure wave hits the ground. Then the ground starts vibrating. So you have 2 sets of effects. One is the primary pressure wave from the blast, and the other one is when the blast hits the ground, nearby ground, the ground also starts to shake. So you have two effects that are transmitted. Then there is unfortunately, there's a third effect, and this effect translates into one force loading and second displacement loading. But then there's a third effect, which when this sum of part of this wave is also reflected from the ground, and this is called the incident wave and the reflected wave. And this reflected wave causes quite often more damage than the incident wave. And to understand that, you have to study the variation of these two, the incident wave and reflected wave pressure, its variation with time. What happens is there's a peak positive pressure and a peak negative pressure for the incident wave, right? And for the reflected wave, you have a higher peak positive pressure and a higher peak negative pressure. That is why the reflective wave is more, what do you call it, dangerous than the incident wave itself. The point to ponder for all of you is, why is it so? I want you to do your own independent reading and let me know. Why do you think the reflected wave is more critical than the incident wave. And there is also, you must also notice that there is a positive wave pressure zone and the negative pressure zone. And remember one thing, this whole incident takes place in milliseconds. Okay. The whole thing takes place in milliseconds, the blast timing. All right. So there is a duration of positive phase and then there is a duration of the negative phase. Both of them need to be checked and ensured that our structure is safe. Now, question is, what kind of design do we do for blast loading? Elastic or inelastic? Yes, please. We come back to the same question. What kind of design do we do for blast loading? Elastic or inelastic?
Inelastic.
Inelastic. Why? Why? Okay. We come back to the same question again and again. Why? The reason you must remember at the base of all the structural engineering is that every load transmits energy or does work on the structure. That means whenever you do work on the structure deforms and the force into displacement is the work done on the structure. And therefore, when the work is done on the structure, that force causes stresses, and therefore, one way to mitigate it, I reduce the forces, is by introducing displacement, increasing the displacement, if it is that kind of a situation. And the other case is I don't like displacement because it is for the user comfort. So I control the displacement and consider a larger force. Now, in the case of blast, what happens is that the magnitude of, do you recall what are the magnitude of pressure we saw for wind in MPa? Very small. Now, to give you some information, imagine that there is a 2.5 tons of TNT explosion and the distance of the structure from such an explosion is 0 to 30 meters. We look at the pressure variation due to the blast being located in this distance, 0 meter to 30 meters. Practically at 0 meter, you cannot design any structure to resist anything. Now, if you notice one thing, at 30 meter, you have about 0.5 MPa pressure due to the blast of 2.5 tons at 30 meters. And if you are around 5, it is way beyond 10, 12 MPa. Okay. So now you compare. Sometimes you have noticed that how does it compare? How does this pressure compare with loading intensity due to live load? If you were to ask, what do you think is the load intensity due to a live load? You have any idea? In terms of, if you have to define an equivalent pressure for live load, what kind of pressure do you think you design for? What is the weight of a Class A vehicle train? Okay, so in kilonewton? Okay, 553. And if you look back at it, the footprint of the live load is around 3 meters wide by 18 meters long, correct? Approximately. So that is 54 square meters, right? So 553, 555.4, so 555 kilonewtons divided by 54 square meters gives you about 10 kilonewtons per square meter pressure, right? And in MPa is how much? Divided by 1000. So 0.01 MPa. Yes or no?
Yes, sir.
And if you look back at it, even a 30 meters away, a blast of 2.5 tons causes around half an MPa. That means what? How many times bigger than your 0.01 MPa? 0.5. 50 times bigger. You design your live load for what kind of design? Elastic or inelastic? Elastic. And you are almost at the brim of your design. So do you think you can design for blast loading, can you design elastically? Impossible.
No, sir.
That's the reason that you always design. You can only ensure that the structure doesn't collapse. Now this is for 2.5 tons of TNT. If you take 1/10 of it, 30 MPa at 1.5 meters. If you take only a 0.25 tons, that is 1/10 of it, then at 30 meters you are coming close to your, instead of 50 times, you may come to about 10 times. And at 1.5 meters, the pressure is around 12 MPa. What does it mean? It is impossible to design any structure for blast load distance less than 30 meters. Now, this is where the biggest question comes. Our code for blast load does not define at what distance you should consider the blast and what should be the magnitude of the size of the. These are the two design parameters which they don't define. It has to be defined by the end user because this is a non-standard loading depending upon the risk associated with such a blast ascertained by the owner of the facility. Okay. However, it's only a theoretical design. Obviously, if somebody knows that a particular structure is designed to resist, say, 1 ton of TNT explosion, he will, to destroy the structure, he'll bring 2 tons. Then what do? You cannot do anything about it, right? So it's important to note that this definition, what is the magnitude of the explosive and the distance from the structure, these have to be defined by the owner of the facility before you are able to carry out even the so-called inelastic or plastic design. Okay. We move on to the one of the last but one of the fourth load, which is the construction load. You have seen some part of it, most of it due to the equipment that operates during the construction phases. Also, based on the sequence of loading, you may have loads of one superstructure or another temporarily. They also got to be considered for it. This is the example seen for a full span loading where the transporter load and the segment load is all to be considered on the superstructure. And this is the place where you are looking at a segment being fed from bottom and is lifted and assembled. So you have one type of loading that is to be considered. So the construction stage loading, it depends upon the construction methodology to be followed. So all of you, before commencing on the construction load analysis, should first agree what should be the construction method. Whom do you agree with? Not amongst yourself, with your contractor client or your contractor, whoever it is, or the owner if he is willing to take the decision. And depending upon that, assess all the load, check all your design for that. So during construction, what are the loads that are possible? Depending upon the construction, you will have equipment load, temporary dead load, unbalanced effects of temporary structure, traveling and launching girder, components carried by the launching girder, thermal effects due to temporary restraints, load due to anticipated soil settlement, and seismic effects on partially constructed structure, which is defined in the code, what you should consider. And the last of the load, which we talked, post loads that we had talked about last time, and now we come to discuss the pre-stressing load. So pre-stressing load in the new code is to be treated as an equivalent external, it's equivalent external force. The only difference between other axially inducing forces and pre-stressing forces, it cannot cause buckling. Are you aware of the fact that pre-stressing forces cannot cause buckling in spite of being a compressive load? How many of you know that? Or how many of you believe that pre-stress can also cause buckling because it's compression? Nobody wants to take a position. Can pre-stress cause buckling? I make a statement, pre-stress can never cause buckling, though it's compressive in nature. How many of you agree? How many of you disagree? Propose. Why do you say it's not an external force? You look at your code. Code is not telling you that it is to be treated as a force only. Yes or no? It is not a different material. You agree or you don't agree that it is pre-stressed concrete is no different from reinforced concrete as a material goes and as a design rule goes. However, there is one significant behavior change with respect to pre-stressing as loads when compared to other axial loads. That pre-stressing doesn't cause buckling. Agree, disagree first. If you agree, why? If you disagree, why? Why doesn't pre-stress cause buckling, though it's axial load? Last time we were discussing buckling. What did we come to a conclusion first? How to initiate buckling? Why does buckling get initiated due to compressive load? What do you need? What's the primary requirement? There must be a deformation from its true axial geometry, correct? And therefore, application of compressive load leads to an exaggeration of that deflection, correct? So now let's come back to our pre-stress load. Let us say we have a pre-stress load like this. When you apply it, what will happen? The girder will hog. Agreed? So therefore, there is an initial eccentricity introduced. But why doesn't it cause buckling? The reason it causes buckling, when it hogs, the CG of the force is on the side. That means this girder will then be hogging like this. The central line will deflect like that. So theoretically, it should go on. Buckling phenomena will lead to an uncontrolled deformation in that direction. Why doesn't it happen? In that direction, it doesn't happen because which side is the gravity acting? That is the CG on this side. But I am saying initial deformation for your axial load is in this direction. Correct? So for this axial component, the exaggeration of the initial deformation will magnify the deflection in this direction, theoretically. But which direction is the gravity taking it? opposite direction. So there is always a resistance from gravity to the other direction. Now that is the case if, let us say, everything is picture perfect. Now let us say other way around. Let us say for some reason we cast this girder with wrong geometry. Let us say we cast this girder itself like this with a small sag. Then the deflected shape will be like this application. Now what happens? Then what will happen? Due to buckling phenomena, this deflection will tend to go this way, right? And when the deflection is going downwards, what will happen to the length of the pre-stressing strand? It will increase or decrease? It will increase. When it increases, what happens to the pre-stressing force in the cable? When the strain in the cable increases, what will happen to the pre-stressing force? Length is increasing, means there's an increase in the strain, right? And if the increase in strain, what happens? The force increases. And if the force increases, what does it do? It opposes this deflection. Because an increasing force will lead towards hogging, whereas the buckling will tend to take it sagging. So in either case, even if it's perfectly cast, your self-weight opposes the action, and if it is wrongly cast, the internal pre-stressing effect on the pre-stressing strand opposes. So there's always an opposition available, which increases with the increasing attempt to buckling. That is why pre-stressed concrete never buckles, though it is axial, it induces axial compression. Okay, so that is to understand that pre-stressing as a load, what is its effect. So the other effect, of course, is in the continuous structure, which we will deal with it when we come to that. I am come to the end, last of the post-based design. In the next class, we will move to displacement-based design, displacement-based loading. So I will stop sharing now, and we have time. Oh, we have only few minutes for question and answers. So if you have question and answers, be quick about it. Otherwise, we'll reserve it for next class. Any questions? If none, then we'll call it a day. Okay, then good night, everybody. I'll see you again next Friday, right? All right.